Continuing with the math unit, now we're going to have to do a couple of calculations. So you need a calculator in hand. And the first calculation is going to be calculating the percent composition by mass. Not by number, but by mass. Any percentage is simply a fraction of a part over a whole times 100, but in this case it's going to be a mass fraction. So when we look up parts here in water, H2O, the hydrogen atoms each weigh 1 AMU, so there's 2 AMUs of hydrogen, and the oxygen weighs to the nearest whole 15.99 is 16 AMUs. So when we add these two parts together, there's the part, here's another part, you end up with a whole of 18. So a water molecule weighs 18 AMUs, atomic mass units. So when we're doing the percent composition, it's the part over the whole. In the case of hydrogen, it's 2 over 18 times 100, which gives us 11.1%. In the case of oxygen, it's 16 over 18 times 100, which gives us 88.9%. And you'll notice that the percentages, by definition, should add up to 100%. That's your check. Even though they never ask you to do more than one of the elements in a compound. All right. For hydrates, again, which are salts with water attached, I want to remind you one more time that the dot does not mean multiply, the dot means add. So when we break down the hydrate, the copper weighs 64 AMUs, the sulfur 32, there's 4 oxygens, which is 4 times 16, and there's 5 waters, so here you're going to have to multiply 5 times 2 if you want to break it down into hydrogen and oxygen. But in this case here, typically when they ask you about hydrates, they're looking for the percentage of water. So it would be a waste of time to do that. It's much better to remember the legal age of drinking water is 18. So water always adds up to 18 AMUs, it's just a good thing to remember. So that's the part in this example. The whole is, when you add this all up, the formula mass of copper sulfate with the 5 waters is called copper sulfate pentahydrate, is 250. So the part over the whole, 5 times 18 is 90. Over 250 times 100 is 36%. All right? That's about as hard as the percent composition gets. Now, you may have done something like this, in fact you should have, in lab, where you heat the copper sulfate pentahydrate in a crucible. Put a little fire under that. And then what happens is that the heat energy breaks the bonds that hold the water molecules to the copper sulfate. And we go from a hydrate to an anhydrous salt. So what you end up with clearly weighs less. And experimentally what you would do is find the difference in mass between before and after, before that you have the hydrate or hydrated salt. And this would be the anhydrous, which means without water. And the difference in mass would have to be the water that was lost. And then you could do a percentage that way experimentally, which is the mass of the water lost over the total mass of what you started with times 100. And that should give you experimentally something close to the accepted value of 36%. And you'll see some problems like that also in old Regents exams. And now let's talk a little bit about the two types of formulas. That is, the difference between a molecular formula and an empirical formula. In a molecular formula, let's just call that the MF, you have the actual number of atoms. In an empirical formula, the EF, you have the simplest ratio of atoms. So for example, H2O2, that 2 to 2 ratio means that there's literally in a molecule of H2O2, 2 hydrogens and 2 oxygens. But that can be simplified to HO. So that's the molecular formula versus the empirical formula. N2O4 can be simplified to NO2. Sometimes you can't simplify it any further, as in the case of NH3, which becomes NH3. So that's going to the right, from molecular to empirical formula. You're just simply dividing, in this case, by the smallest of the numbers to get the empirical formula. So if somebody gave you, like, for example, C6H12 or C6H14 better, make that clearer. So again, in this case here, you wouldn't divide by the smallest of the numbers because you wouldn't get whole numbers. So in this case here, this can simplify if you divide each of these by 2 into C3H7. That can't be divided any further or simplified any further. Now if you went backwards, if you had an empirical formula, there are many possibilities for the molecular formula. You could have the C2H2 as one possibility, C3H3, C4H4. Now it's possible that some of these don't exist, since what we're doing here is just mathematics. Now to find out which one of these is the actual molecular formula, then you'd have to take it a step further, as you have here. You're given the empirical formula of the compound CH. And you're asked to find what the molecular formula of that compound is if it has a formula mass of 78. So we're going to have to find out how many times does the mass of CH go into 78. So first of all, find what the mass of CH is. A carbon weighs 12, a hydrogen 1 AMUs, so that's 13 AMUs. And simply divide the formula mass that they gave you by that 13 to get 6. What that means is to take the empirical formula they gave you and multiply it by 6. So 6 times CH is C6H6. All right, why don't you try doing this one right here. We're told the empirical formula of the compound is CH2, the EF, and its formula mass, the FM, is 42. Find the molecular formula. So again, let's find out, first of all, what CH2 weighs. That would be 12 plus 2, which is 14. Then let's divide the 42 by that. 42 divided by 14, our second step, would be 3. And that simply means take that empirical formula, multiply it by 3. So 3 times CH2 would give you C3H6 as your final answer. So that was pretty simple. And then, as far as calculations are concerned, you're going to have to do a mole calculation, I'm sure, on a Regents exam. So let's look at that. So you should turn to the back in Table T, where you find the mole calculation formula. Again, it is that the number of moles is the given mass divided by the GFM, the gram formula mass. So that would be the formula mass expressed in grams. Again, what is the mass we're asked here? What is the mass of 2.5 moles of NaOH? So we're given the 2.5 moles, and we're given a formula. If they give you a formula, you can certainly find the gram formula mass. Na in your periodic table is about 23 AMUs. Oxygen's 16 and hydrogen's 1, so they add up to give you a gram formula mass of 40. That is 40 grams per mole, which means that a mole of NaOH, a specific quantity of NaOH, chemists always operate in moles, just as bakers operate in dozens, and grocers work with, when they deal with produce, they use a gross of apples, a gross of bananas. So each industry has its own unit to convey quantity. So in the case of chemistry, they use the moles. So a mole of NaOH is going to have a mass of 40 grams, and 20 grams therefore would be half a mole of NaOH, and if you double that, 80 grams would give you 2 moles of NaOH. Anyway, in this case here, they gave us, what is the mass of 2.5 moles of NaOH? Well, since 1 mole weighs 40 grams, then 2.5 moles would be 2.5 times that amount, or if we plug it in, the number of moles is 2.5, X is the mass that we're looking for over 40, and 2.5 times 40 is 100 grams. So they could either ask you, what is the mass of a certain number of moles, or they could ask you how many moles are present in a certain number of grams. So here they gave you 160 grams of the same compound, NaOH, so the given mass is 160. The gram formula mass hasn't changed, so 160, if you want to enter the units, grams, divided by 40 grams per mole, 160 divided by 40 is 4 moles. And that works out real nice. So that's as deep as it gets with the mole calculation. And most of the time, just rounding off to the nearest whole number will be sufficient. Okay, you can put your calculators down. That's pretty much it. On the next page, we'll do a little more using your calculator, but let's end this page here, this page in the math unit, with a little balancing. Now, balancing chemical equations is certainly not a favorite of students, and it's either you love it or you hate it, I should say. All right, and I wouldn't stress on it if this was not your favorite. Remember, on the Regents exam, there'll only be one question on this. All right, so you have plenty of questions to do well on, and you could punt on this one if you're totally clueless, but you shouldn't be. All right, because when you read a chemical equation, you should read from left to right. All right, and if you take one element at a time, then you'll see that it's very simple to get the proper coefficients to give you a balanced equation. All right, the reason why chemical equations have to balance is because there needs to be a conservation of mass. In other words, mass cannot be lost. The total mass or number of atoms of products and reactants must be the same. Nothing disappears in a chemical reaction. Now, you want to remember that the coefficient of 1 is assumed, though. So the numbers in front here are the coefficients. The small numbers on the script line are the subscripts. And you're not allowed to change the subscripts in an unbalanced equation if you want to balance it. And you can't add to the equation. So in this case here, if you had said H2 plus O2 should give you H2O2, well, that's true, it does give you H2O2, but not in this form, not in this equation here. So another temptation you might have is to add to the equation. Since we're missing an oxygen, you might say, well, it produces H2O plus oxygen. Well, you can't add to the equation either. The only thing you could change is the coefficients. So if we take them one at a time, let's see what we can do. There's 2 hydrogens here, so right away I look to the right to see if there are 2 hydrogens, and that's balanced. And there are 2 oxygen atoms, as indicated by this subscript, and there's only 1 here. So what you want to do is right away take care of that imbalance by placing a coefficient here of 2. So that 2 now multiplies the hydrogen to give you 4 hydrogens, and the oxygen to give you 2 oxygens. So since you now have 2 oxygens on the right and 2 on the left, that's good. But 2 times 2 will give you 4 hydrogens. You only have 2 on the left side. So that means you have to go back and change this to a 2. So to add up the atoms, we'd have 2 times 2, 4 hydrogens, 1, the coefficient of 1 is assumed, 1 oxygen. 1 times 2, I should say, 2 oxygens, forgive me. And then 2 times 2, 4 hydrogens. And 2 times 1, the subscript of 1 is assumed, 2 oxygens. And so clearly this thing balances because the number of atoms on both sides, 4 hydrogens, 2 oxygens, 2 oxygens, is the same. All right, let's try doing this one here. Oh, before I forget, sometimes they make this into a multiple choice question. Now I'll ask you, when the equation is balanced, what is the sum of the coefficients? Adding all the coefficients on both sides. So 2 and 2, but don't forget the 1 that's assumed is going to give us 5 in this case. All right, let's try this one here. 2 nitrogens. Right away, go to the right side of the arrow. 1 nitrogen. So take care of the imbalance right there. Now that you're here, stay here. That will give you 2 nitrogens, but 2 times 3 gives you 6 hydrogens. You only have 2 on the left side. So multiply that by 3, and you'll get 6 hydrogens. So we have 2 nitrogens, 2 nitrogens. 3 times 2, 6 hydrogens. 2 times 3, 6 hydrogens. Remember, it's always the coefficient times the subscript is going to give you the number of atoms of each element. Okay, let's try this one here. Again, for the sum of the coefficients, it's 2, 3. Don't forget the 1. I'm not going to write it in. And that's going to give you a sum of 6. Now with this equation here, my suggestion is right away, if you stand back, you'll look at it and notice that there's a nitrate ion here, which is a poly, and a nitrate here. And it's easier just to think of the polyatomic ion as one particle. So in essence, what I'm saying is there's 1 nitrate here, and there's 2 on the right-hand side. So right away, the copper's balancing, the silver's balancing, but the nitrate isn't because there's 1 here and 2 there. So you got to fix that. And placing a 2 here multiplies the nitrate, but also the silver. So now you have 2 silvers on the left, and 1 on the right, so fix that. And now you have a completely balanced equation. So 1 copper, 2 silvers, 2 nitrates, and 2 nitrates here. And the sum of the coefficients here happens to be 6 again. Okay, let's go to the last page on mathematics. This is a pretty short unit, but this is all that's really tested, so I'll meet you there.